Okay, so we have looked at a couple of graphical representations of descriptive statistics. Now, in the second part of Module 2, Module 2b here, we're going to take a look at some numerical descriptive statistics. What are we hoping to get out of this? Well, one thing we're hoping to get is just some practice using the ISLE tool that we're doing statistical analysis with. Of course, you can use things other than ISLE, but I really encourage you to get used to using ISLE because it's very easy. It's very thorough and complete and nice as far as what we need in this course. Also, it has the advantage of, if you are using ISLE, then your submissions as far as homework and worksheets will look like other people's and make it easier for our TA to look at. We want to interpret the mean and the median and be able to decide which of them is more appropriate for a given data set as a so-called measure of central tendency. That is, the measure of where the center of the data is. Now, whether the mean makes more sense or the median makes more sense is affected by what's called the skew of the distribution. That is, whether the distribution is stretched toward positive values or stretched toward low values or negative values. We're going to talk about some measures of variability and why these things are important and how to compute them. In particular, we're going to take a look at the variance and the so-called standard deviation to describe the variability in data. We also want to take a look at the so-called empirical rule for estimating what you think the standard deviation of a data set probably is without bothering to crank out the numbers. And we'll explain why that matters as we progress. Okay, so there are a variety of measures of what the center of the data is. One that we've already talked about is the median, which is literally the middle point of the data, and another very common one that we probably think of as being the average value of the data is the so-called mean. In terms of measuring how the data varies about the center, one thing you can describe is just the range of the data. That is, how wide the data are from the lowest value up to the highest value. If I have in a data set, if I have a median value of 10, meaning half the data are below 10 and half the data are above 10, and my range is 2, let's say, okay, well, if the median is 10 and the range is 2, that means I have a very clumped distribution right around that median value of 10. On the other hand, if the median value is 10 and I tell you that the range is, let's say, 60, well, that's an enormously wide range. It might go down to 0 or even negative values, and it might go way up to 30, 40, 50 on the, or 60 on the positive side. So the range doesn't, the range describes the distance from the minimum value to the maximum value, but it doesn't really tell you much about any other structure of that variability. The interquartile range that we discussed in the previous section is a little better because that tells you where the middle 50% of the data are located. Also, what we often use computationally are this thing called the variance, which is the sum of the squares of the differences between a particular data value and the mean. And the square root of that is called the standard deviation. The sample variance is usually denoted as s squared, s for s for standard deviation, and s squared is the square of that. And then the standard deviation is the square root of the variance. All right, so in terms of doing these by computation, you very likely already know how to do these. The mean is what we think of as the average of all of the values. That is, if you have n observations, let's say you have n observations of people's weights, n observations of people's heights, n observations of people's blood pressure, n observations of people's income, whatever, and you want to find the mean, well, all you do is add up all of the individual values and divide by the number of observations that you've made. And we usually use the notation x bar to represent that mean of this particular sample of data. Okay, now if this is our particular data, 1, 1, 2, 2, 2, 3, 4, 4, 5, 6, we've collected data representing something and then we've put it in order to make it easier to deal with, at least as far as the median is concerned. Notice that these extreme values, in this case the value 16, has an oversized factor of influence on the mean value, okay? So if we add up all of these values in our example data set and divide by the number of values, we compute a value of 4 as the mean. And yet, if we look for the value 4 in the data, notice that 6 of these 10 values are less than 4, and only 4 of these 10 values are greater than or equal to 4. So because of this so-called outlier value 16, the mean is perhaps artificially brought up. Now, whether an outlier is artificial or not is you have to figure that out on a case-by-case basis depending on what you're analyzing. Now, the median, if you have an odd number of observations, is simply the mean of the middle two values. Here we have 10 observations. The fifth and sixth observations are 2 and 3, and so our median value is 2.5. The question is 4 a better representation of the middle of this data, or is 2.5 a better representation of the middle of this data? Well, it's up to you to decide. The skew is the amount of data, or is the data that are far away from the center. Okay? If a data set is skewed, that means that there is a lot of data that's far away from the center. If the data is not skewed, that if the data is symmetrical, then using the mean is the right thing to do. And in fact, the median and the mean will be the same for truly symmetrical data. All right, so let's take a look at our histogram of the weights of people in our fast food study. Show the toolbox. Do a histogram plot of weight. And we saw that this is right skewed. In fact, a box plot makes that even more obvious. So we might argue that using the median value is a better representation of the center of this distribution as opposed to using the mean value. How do you decide? Well, you can compute both the median and the mean for any given data set that you're looking at If the two are pretty close to each other, like within 5% of each other, then you can ignore the skew and go ahead and just use the mean. On the other hand, if the median is, let's say, more than 20%, either above or below the mean, then you have what you'd call a highly skewed data set, and you're probably better off using the median as the representation of the center of your data. Now, in between here, well, you've got a moderate skew, and so now you just have to, make a decision about what you would rather think about as the center of your data. This is, frankly, subject to individual interpretation. So, we call a distribution symmetric if the mean and the median are the same. That is, given the mean, if the number of observations below the mean and the number of observations above the mean are about the same, then the median will be the same as the mean, and that creates a symmetrical kind of distribution. On the other hand, if you have a right-skewed data set, that's being shown here for the ages of the people in our fast food test. Let's confirm that. I'm going to plot the age instead of the... Okay, so here we have the ages of people at the Subway shop on Craig Street. And notice that the vast majority of the customers of the Subway shop on Craig Street are students from either CMU or Pitt, and so they're mostly around 19 to 22 years old, and then we have some ancient professors like me up here in the mid 60s or so, and there are some people who work in the area of Craig Street who are more middle-aged, and of course there are a lot of more middle-aged professors at CMU and Pitt as well. So this is an example of right-skewed data. The mean is significantly greater than the median in this case. If the plot looked the other way around, then that would be a negatively or left-skewed data set. This slide shows the income distribution. Sorry, that's a pretty ugly highlight. This is the bottom 98% of households in the United States in 2005. And what we see is that this is a very heavily right-skewed data set, or positively skewed data set. The median household income, and again, this is 18 years old, so these numbers are both of these numbers are higher nowadays. The median income, the income where half of people have that income or lower, and half have that income or higher, is 46,000 and some, whereas the mean is 63,000 and some. All right. Now, that means that the ratio of the median to the mean is only 0.73. That's quite a ways lower than 1. And so if we're doing analysis of average households, we're probably better off thinking in terms of median income rather than mean income for things like tax policy and healthcare policy and transportation policy and things of that kind. By the way, it turns out that virtually every country in the world has an income distribution very similar to this. And there are a lot of social and mathematical theories as to why this is. But it turns out that this is a very common kind of income distribution. Okay, here we have an example of a data set where most of the data looks nicely symmetrical, but we have a few outliers out here at the extreme right. If we look at all of the data, including the outliers, then our median value in this data set is 10. And our mean value is 12.4. So the mean value is 24% higher than the median in this case because of inclusion of these outliers. If we eliminate the outliers, then the mean and the median are quite a bit closer to each other. So the question is, should we eliminate the outliers? And this is a big, huge, important question because depending on your particular case, sometimes the answer is yes, sometimes the answer is absolutely not. To illustrate, let's suppose that we've got many people collecting data for a particular statistical experiment, and one of our data collectors accidentally writes down a value that's 10 times larger than it's supposed to be. So this one data collector writes down these values 38, 44, 48, when what this data collector should have written down was 3.8, 4.4, and 4.8. In this kind of situation, these outliers are errors, and you are completely justified in throwing those outliers away and using the rest of the data to do your analysis. On the other hand, let's suppose that you're doing something like financial analysis or a medical study, and these values here represent returns of an investment or the negativity of outcome of some kind of drug. Well, in finance, if this is financial data, extremely large or small returns are rare, but do occur. And so if these are extremely large but rare returns on some kind of stock, these are actually the most influential data points in terms of the overall performance of your portfolio. And you do not want to ignore these rare high returns. Okay? This is where you are either making or losing most of your money. So if these outliers are on the negative side, you're in really bad shape. And in that case, you really, really, really don't want to exclude these outliers. Similarly, in a medical study, maybe these outliers, these are the people who developed extremely high fevers and died. Well, again, you better not eliminate the outliers in a situation like that. So whether to include or exclude outliers when you're doing statistical analysis depends very heavily on what it is you are analyzing, how it is you have collected your data, and so forth. All right. Now, why do we need to care about these measures of variability? Well, for one thing, we want to be able to say something like, we believe that the average return on the S&P 500 over time is 7% above the inflation rate, and we are 95% confident that that is true. Now, if we don't have some kind of justifiable measure of variability, then we cannot say with any confidence, we cannot say that we're certain of the return of the S&P 500 over time with any kind of confidence. All we could say is, well, we're pretty sure that over time the S&P 500 is going to return 7% above inflation. If you have a customer and you're responsible for investing their money, they're not going to be very impressed when you say you're pretty sure. Okay, so we need to have some rigorous and consistent way of measuring the variability when we study data. The measure of the center of the data is also called the expectation or expected value of the data set. The expected value is the mean by definition, not the median when used in calculations. And the variability measures how much risk there is in our expectation, or how much uncertainty or variability there is. Well, yeah, variability measures variability. How much variability there is around our expectation. Okay, so you will hear this term expected value as another way of describing the mean of a particular set of data. Variability matters at least as much as the mean does. Here we have a sign on a lake saying that the average depth of the lake is 3 feet. Well, that's all very well, but if you go walking out into the lake, just knowing that the average is 3 feet doesn't mean that there isn't suddenly a drop-off to 30 feet at some point in the lake. Okay, so 3 feet tells you an average of how deep the lake is, but the variability here would tell you that, oh, by the way, if you go walking around out here, you could drown. So let's discuss an example illustrating variability. You are in some scenario, okay, you have come to me and I am going to make you an offer. One offer I might make to you is I will give you $5,000 for sure, period, end of discussion. Okay, you come into my office, I say, I'm going to give you $5,000. Do you accept? What is your expected profit from this deal? What is your risk from this deal? That is, what is the mean dollar amount that you expect to get if you take this deal? Well, it's going to be $5,000. It's going to be the sum of all the possibilities divided by the number of possibilities. In this case, it's just going to be 5,000 divided by 1, and so the expected profit here is $5,000. And what is the risk in this scenario? Well, there's no risk. You know, assuming I'm not a liar and assuming I actually have $5,000 to give you. Okay, so there's no risk. And would you take this offer? I hope to goodness that you will say yes. All right, so you walk into my office. I say, I'm going to give you $5,000. And you say, yes, thank you very much. And you take your $5,000 and leave. Now, another person walks into my office. And I say, okay, I am going to flip a coin, and I promise you that the coin is fair. That is, the probability of getting a head is exactly equal to the probability of getting a tail. They're both 0.5. If we get a head, I will give you $50,000. But if we get a tail, you are going to have to pay me $40,000. Okay, so in this scenario, what is the expected profit? This is a little trickier to figure out, but you've got a 50% chance of receiving $50,000, a 50% chance of losing $40,000. So the expected value here is going to be 50,000 minus 40,000 divided by 2, because there are two possible outcomes. Okay, so 50,000 plus minus 40,000 is 10,000, and then divided by 2, because there are two possible equally likely outcomes, is $5,000. So the expected profit from this deal is also $50,000. Also $5,000, excuse me, okay? So 50,000 in one situation, minus 40,000 in the other equally likely situation. Divide that by 2 and you get 5,000. What is the risk? Is there any risk here? Oh yeah, there's big time risk here. Because if I get a tail, I'm going to get that $40,000 from you one way or the other. And, and this is going to be a problem if you don't have it. So would you take this offer? Okay, so this is kind of a central question in finance, actually. Would you take this offer when the expected profit is a large positive number, but the risk is significant, and you could lose a lot of money? I'm going to make a wild guess that you, as a probably semi-impoverished student, would not take this deal. You would not take this offer because it is much more frightening for you, the prospect of having to come up with $40,000 that you would lose versus the possibility of winning $50,000, even though the probabilities of those two outcomes is the same. Okay, this, by the way, is what's called risk aversion. Most people are risk averse, and if the probability of losing a lot of money is near the same as the probability of winning money, most people would stay away from that kind of bet. Now, on a purely expected value basis, these are equivalent offers. Me giving you $5,000 is mathematically equivalent to me offering you this gamble. But one of these offers has a very lot of risk associated with it, and the other has no risk at all. Okay. So, how do we measure this variability? There are various ways, and I mentioned them earlier. One way is the range of values, which isn't really that helpful. In our example data with these 10 values, 1 up through 16, if we just take the highest value and subtract the lowest value and say, well, the range of values in here is 15, I'm not sure what you do with that. I mean, that tells you that there's a fairly significant range, but only knowing the range doesn't tell you, are those values kind of lumped up closer to 15, or are they kind of lumped down closer to 0? It's not a too... I mean, it's a fact that the range here is 15, but it's not too useful figuring out how to make a decision with that information. The interquartile range is much more interesting. It tells you that in this case, the range of the middle half of data in here is just 2. So that implies that the range is the interquartile range is fairly narrow. The data are kind of lumped up around kind of lumped up around the median in this case, because the outlier here stretches the mean out to 4. Other computations that we often use in statistics are what are called the variance and the standard deviation, which is simply the square root of the variance. To compute the sample variance, okay, and this is not, I'm not trying to justify this in any way, I'm just saying that this is what you do. What you do to compute the sample variance first is to compute the mean of the sample. Okay, then you go back through your data, and for each data value, you take that data value and subtract the mean. That will result in either a positive or negative number. When you square that result, you will definitely get a positive number. Okay, so the variance is guaranteed to be a positive number because we're squaring this difference. Then we divide the sum of those squared differences by the number of values minus 1. And I will tell you why you use minus 1 and minus 1 here without trying to actually do a proof for you. The sample variance computed in this way is what's called an unbiased estimator of the true variance of the overall population. All right, so reaching back to what I mentioned in Module 1 in our intro module, let's suppose that we are trying to find the true mean of all of the household incomes in China. All right, that true mean is what we're going to call the Greek letter mu. But we don't have the time or the money to go out and gather this data from, over 400 million households. So what we'll do instead is to compute a sample mean, an X bar, by just looking at a sample of households and adding up the incomes of those sample households and dividing by the number that we test. Maybe we take a sample of 1,000 and we just add up those incomes and divide by 1,000, and that gives us our sample. There is going to be variability both in the entire population and in the sample that we take. And it turns out that because you're using a sample, you have to use this kind of fudge factor of n minus 1 in your denominator to account for increasing uncertainty in your sample variance as your sample gets smaller and smaller. Now, as n gets larger and larger and larger and approaches the 400 million or 450 million or whatever number of households, then the difference between 450 million and 449,999,999, I mean, that difference is pretty close to zero. But because we are less certain of the variability when we just use a sample, we throw in this fudge factor n minus 1. All right. So by saying that this is a fudge factor, I'm probably making it sound like this is just made up out of thin air, and that's not the case. You can do a mathematical proof by defining the bias between the sample variance and the true population variance as a difference of expected values. And that difference of expected values should approach zero as the number of samples that you take increases. But if the number of samples is small, then you really can't say very much. You can't say with great accuracy what the variability is. Let me give you another concrete example, which hopefully will help you intuitively remember that you'd better subtract minus 1 when you compute a sample variance. If I tell you, and I don't know the actual number here, I should find out the actual number. Let's find out what the height of the Empire State Building is. All right, so we'll take the height to the tip. The height of the Empire State Building is 1,454 feet. Okay? So, if I ask you, what is the average height of the Empire State Building? Well, there is only one. The entire population consists of one Empire State Building, and so the average height of the Empire State Building is 1,454 feet. Now I ask you, what is the variability in the height of the Empire State Building? And without resorting to craziness like, maybe it grows or shrinks according to temperature, there's no variability. I mean, the height of the Empire State Building doesn't vary. It is this number. It has no variability, and therefore its population variance is going to be 0. Okay, now let's change things. Instead of asking you what is the and by the way, let me back up here. This is very similar to the two scenarios that we talked about here. In one scenario, I give you $5,000. In another scenario, I'm going to flip a coin and give you an expected $5,000, but there's risk. All right, now let's suppose instead of having the entire population be the one and only Empire State Building, I say to you, okay, I want to know about skyscrapers in Manhattan in New York City, the island of Manhattan in New York City. The Empire State Building is 1,454 feet tall. What can you tell me about the mean and the variability of skyscrapers in the island of Manhattan? And you're going to look at me like I'm some kind of a nut. What the heck are you talking about? You want to know the mean height of skyscrapers in Manhattan, but you've only given me a sample of one skyscraper. So fine, I can compute that the mean of skyscrapers in New York City from this one sample building is 1,454 feet. What is the variability of the heights of skyscrapers in Manhattan based on this sample size? Well, what in the world are you talking about? You've only given me one sample. I can't say anything at all about the variability. And notice that this works out nicely because the sample variance has n-1 in its denominator. And if you only have one observation in your sample, then the variance just blows up. It can't be computed. So it's ridiculous to even talk about what is the variability of the heights of skyscrapers given that you've only provided me with the height of one building. Okay, so that's kind of ludicrous. All right, so I finally agree with you after you've done your analysis and presented to me your analysis. I agree with you. Okay, I get it. Okay, that's ridiculous. I want you to tell me the average height of skyscrapers in Manhattan. And I'm going to be nice to you now. And I'm going to tell you that the height of the Empire State Building is 1,451 feet. And the height of the Chrysler Building is 1,046 feet. Now what can you tell me about the average height of skyscrapers in Manhattan and the variability of the height? Well, it's still pretty ridiculous. Now I only have two observations. I can compute a mean. Okay, what do we got? 1046 plus, what was it, 14. Let's pretend it's 1454. So that works out purely by accident to be exactly 2,500. And so I'm going to tell you, okay, the mean, I calculate that the mean height of skyscrapers in Manhattan is 1,250 feet. And now you're going to ask me, what's the variability of that? Well, there's a huge variability because, you've only given me 2 items in my sample. So I now have the ability to compute a sample variance. But the sample variance is going to be huge. So I've got 1,454 minus 1,250 squared plus 1,046 minus 1,250 squared. I've got the sum of those 2 numbers squared divided by 2 minus 1 is 1. All right, so that's going to be a large variance to to make up for the fact that you've given me such a ludicrously small sample size. Now, as I tell you more and more and more and more heights of more and more and more and more skyscrapers in Manhattan, my mean is going to get closer to the truth, and my variance is going to get narrower and narrower and narrower because the n minus 1 gets to be larger and larger. And eventually, this sample variance, the sample mean will equal the population mean once I tell you the height of every single skyscraper in Manhattan. That's the whole population. And the sample variance will be really, really, really close to the population variance, which is calculated the same way, except just divided by n instead of by n minus 1. All right, well, that was a little long-winded, but I hope it gives you, remember that you'd better divide by n minus 1 when you're taking a sample instead of just dividing by n. Now, what is one problem with the variance? One problem with the variance is that it's not in the same units as the mean. The mean, we said here, was 1,250 feet. But the variance, because this is a sum of squares, the variance here is going to be in feet squared. And it's really hard to think about what the meaning is of feet squared. So we normally take the square root of the variance to compute, and that gives us, come on now, highlighter, you can work. Okay, for some reason I can't highlight that square root sign. If we take the square root of the variance, that gets us back to just plain feet. And it's easier to think about the variation around the mean when the variation is expressed in the same units as the mean. Okay, so based on our example data set, 1, 1, 2, 2, 2, 3, 4, 4, 5, 16, we can compute that the mean is 4. We can individually compute the deviations from the mean. Okay, that is the individual x sub I values minus the mean. We square those and then add them up, divide by n minus 1, and that gets us this value 176 over 9. That is the variance, that is the sample variance, which is the square of the standard deviation. And so the standard deviation here is 4.42. Okay, so the standard deviation is more meaningful because it's in the same units as the mean is. The mean value is 4, but there's a fair amount of deviation around 4 because of that outlier primarily. Notice that the outlier's contribution to this sample variance is enormous compared to everything else. Here is a diagram showing kind of what the difference looks like when you plot a distribution in terms of a distribution that has a small standard deviation versus large standard deviation. Okay, now what do we mean about big versus small? Well, again, it's kind of a matter of experience and judgment. But if you have a big standard deviation, that means that the distribution is going to be spread out horizontally. If I have a small standard deviation, it will be more peaked and more centralized. One of the most important distributions that we have is called the, okay, I guess we're not using the word normal distribution yet. But in a so-called normal distribution, it turns out that 68% approximately of values fall within plus or minus 1 standard deviation of the mean, and here we're talking about the population mean. Roughly 2/3, in other words. So roughly 2/3 in a so-called normal distribution, roughly 2/3 of the values that you get that you measure will fall within 1 standard deviation of the mean. 95% will fall within approximately 2 standard deviations. And 99.7% will fall within roughly plus or minus 3 standard deviations. Okay? Now, we can use this knowledge combined with making an assumption about the normality of some data that we're looking at to empirically compute what we think the standard deviation probably is for a given population. I want to be clear that this is an estimate of what the standard deviation probably is based on an assumption that the underlying distribution is more or less a normal distribution. Okay. So here, if we look at our histogram of people's weights for our fast food experiment, okay, I want to see a plot of the histogram of the weights of our people. Here we go. We can compute what the mean is, and we can compute what the sample standard deviation is. Let's do that. We're going to compute what the mean and the standard deviation is of the weight, but excluding missing values. We don't know how to do computations with data that we don't have. We'll calculate that, all right? And so we've got a mean of 163 and a standard deviation of 36.7. That means that the mean is around 163. And if we add 1 standard deviation or subtract 1 standard deviation around the mean, that should be approximately 2/3 of the values. And it turns out that it is approximately 2/3 of the values. In our case, it's 73%. 2 standard deviation ought to be approximately 95%. And in our case, it turns out to be 94%. And then 3 standard deviations ought to be 99.7%. We don't quite have 99.7% here, but 97% is still what we might call, most of the values. All right, so again, this is just an example illustrating the idea that most of the data, almost all of the data, will fall within 3 standard deviations above and below the mean. What does that imply? Well, what it implies is if we estimate what the range of some population is, we can then make an assumption that the standard deviation is going to be approximately 1/6 of that range. Why can we do that? Well, here in this illustration, notice that we have approximately 2/3 of the values around, between plus and minus 1 standard deviation, approximately 95% of the data around plus or minus 2 standard deviations, and almost all of the data around plus or minus 3 standard deviations of the mean. So, if we estimate what we think the range of heights of most men are, we can then just divide by 6 to get an estimate of the standard deviation of heights of men. And I know this seems kind of magic, but it's a very good first guess at a standard deviation for something. All right, so let's suppose we decide that, well, the vast majority of men are 5 feet or taller. And the vast majority of men are 7 feet or shorter. Even without doing any scientific sampling, we're going to say, okay, everybody I've ever known, everybody I've ever seen, I'm willing to say that there's, like a 99% chance, 99 out of 100 men that I'm going to check their heights are going to be between 5 feet tall and 7 feet tall. All right? Well, we now can just compute the range of that height difference. Okay, and that's 24 total inches. If we divide that by 6 standard deviations, we get that based on our guesstimate that 99% of men have heights between 5 feet and 7 feet, that implies that the standard deviation is probably about 4 inches. Okay? Okay, so let's see whether this empirical rule, this notion for guessing what you think the standard deviation of some population is, let's see if this makes any sense. Let's try for our fast food data. We've already evaluated the weights of people. Let's and we've talked about an example using heights of men. Let's look at age of people and see if we can make a reasonable guess as to what the standard deviation of ages would be at this Subway shop. Okay, well, we know that customers at the Subway shop are, for the most part, going to be students and a few business people and professors from the nearby universities. I think it's safe to say that young teenagers are not too likely to be buying stuff at Subway, and really elderly folks are not too likely to be buying stuff at Subway. So let's suppose, I'm going to estimate, all right? This is my personal estimate. Your estimate may be different. But I'm going to say that 99% of people buying stuff at the Subway shop are between the ages of 15 and 75. Okay, now we've actually seen the histogram of ages. We saw that a while ago, and we saw that it was very skewed and centered around 20 or 21 years old. So let's see whether my estimate here makes any sense, not in terms of the mean, but in terms of the standard deviation. So let me compute the... Oh, I have to pick some data first. Let me pick age, and I want to compute the mean and the standard deviation of the age, excluding any people who didn't provide their age. Let's see what we get. And cool. Okay, so we get told that the mean age is 28.8. The standard deviation of the ages is 12.627. So in fact, the standard deviation is larger than my estimate of 10. I forgot to show you how I got that estimate of 10. Well, it's fairly easy to do in your head. If we figure that the range goes from 15 to 75, and you subtract those, that means that you've got a 60-year range between the youngest person and the oldest person in this 90% range. And then if you divide that by 6, you get 10. Okay? So I estimated that the standard deviation of the ages of people in this restaurant was probably about 10. And it turns out my estimate was a little too low, but not completely ludicrous. If, without looking at any data at all, I was able to get kind of close. I was able to get within 25% of what the standard deviation actually was. Let's also show a histogram of the ages as well. Okay, so the mean is 28. So the mean is skewed up well above the median. The median is down around 21 or 22. But because look at this. We've got someone, wow, cool. We've got 2 people between 84 and 85 who bought sandwiches. I tell you, some of those professors just hang on forever. Okay. All right. So that's what the empirical estimation of standard deviation is about. Here are a couple of other examples. Let's look at this second one. Some sport is going to be the most popular sport in your country. Okay, in the United States, American football is probably the most popular sport, although basketball is also very popular, baseball is very popular, hockey somewhat less so. So what sport do you think in your country is the most popular sport? Can you guesstimate the standard deviation of the ages of people at the championship game for your sport using this so-called empirical rule? In other words, you're going to make an educated guess as to what you think the total range of ages is going to be. You take that range of ages, divide by 6, and that's going to give you an estimate of the standard deviation of the people in the stadium. Okay? Well, I'm not going to do that computation for you because I don't know what your sport is or what your opinions are about ages of people at the event. All right, well, that gets us to the conclusion of looking at some numerical descriptive statistics about data that we've collected.